Today we're going to talk about groups. Groups are sets with one operation that satisfies some axioms, a lot like a ring or a field. It doesn't mean that we can't put more than one operation on the set, just means that we're focusing on one at a time. Usually we name the operation that we're looking at, and sometimes we write it multiplicatively just by writing elements next to each other, or maybe we'll use a fancy symbol like a star. Either way, what we want to notice is that this operation, juxtaposition, or the star, should satisfy four axioms. The axioms are G1, closure, G2, associativity, G3, identity, and G4, inverses. And you should remember that when we talked about rings and fields, we had these things for addition, and we called them A1 through A4, or multiplication, and we called them M1 through M4. The difference here is we don't know whether we're talking about addition or multiplication or some other crazy operation that we just defined, like function composition. So we don't want to name them A or M, we're just going to call them G1 through G4. A couple notes here. We tend to call the operation's identity the letter E in a general group. And if our group is commutative, meaning it satisfies G5, we're going to call it an Abelian group for the mathematician Abel. Now, because groups have less structure, they can be really, really weird. Okay, time for some examples. Now, I've posted these notes for you, so you should take a look at them in more detail, but let's look at number 2 for a moment. If I take a ring that's non-trivial, so it's got, more than just the 0 element in it, then if I just look at its addition, it's a commutative group. Shout out to Abel. Anyway, if we look at its multiplication, the problem is that 0 doesn't have a multiplicative inverse, so it's not a multiplicative group. If we think about subrings, and especially ideals, an ideal is an additive subring of our group, and so it is also an Abelian group under addition, but multiplication fails for the same reason. If we wanted to fix the ring to make it a group under multiplication, we could throw out 0, right? So if it's and I guess we'd need to know that it's a division ring so that every non-zero element has a multiplicative inverse. In that case, we do get a multiplicative group. Just like in number 3, remember, a field is a commutative division ring. Now, I've also pointed out here that number 6 is going to be a really important example for us. It's the set of roots of unity, and what we want to notice about them is that it's closed under multiplication and every element has an inverse and it's associative and all that good stuff. So, nth roots of unity form a group under multiplication. So take a look at these examples, post any questions that you have about them on Piazza. Alright, let's be smart about this for a second. We've seen the definition of a group. We know that it's a set with an operation that satisfies 4, maybe 5 axioms if it's Abelian. What do we think we're going to get next? Well, we're probably going to get the properties of groups proposition. And after that, we'll get the what's a subgroup definition. And after that, we'll get the how do we prove something's a subgroup without doing so much work? But spoiler alert, groups are pretty simple. So it turns out that it's actually pretty easy to show something's a subgroup just from the definition. After that, we should anticipate that we'll see group homomorphisms. How do we know if two groups are similar or compatible, or even the same? That will give us group isomorphisms. Anyway, get ready. Here comes the properties of groups proposition. Alright, so we're going to look at the additional properties of groups here, and we'll prove some of them, and I'll leave some of them as exercises for you. So let's prove 1, that the identity is unique. We'll do that by supposing that we have two different identities, E and D. Well, then we've got ED equals E, by the definition of D being an identity, and similarly ED is D, because E is also an identity. Now we have E equals D. And that's the way these proofs go, so I've added a couple little hints in blue here for the sample proofs already included on the slide, and you should try the other proofs too. I said you should use A1 through A4, I mean G1 through G4, but I'm thinking additively because we're going to talk about Abelian groups next. When we look at an Abelian group, we tend to write the operation as addition, because addition, the way we're used to it, behaves additively, right? We've got a 0, a negative, we've got all sorts of good stuff. More generally, for groups, if we know that they're coming from a ring and we're looking at multiplication and throwing out 0, then we'll use multiplication, and the identity will be 1. But otherwise, we'll stick to the E inverse, A inverse, juxtaposition notation. Now for the star of our show, the Galois group. Remember that our Galois group is a set of automorphisms that preserve a bunch of stuff. Now, the operation we're going to use is function composition, and that's up there at the top of the slide. It's f composed with g is a function from k to k, where it just means that we plug in k to f composed with g for all k and k. That's our function, f of g of k. Now, in this set builder notation down here describing the Galois group of k over f, we've got that f preserves addition and multiplication. That's what it means to be a homomorphism. It's one-to-one and onto, so it's an isomorphism, and in fact an automorphism. And the last thing says that it fixes the base field f. So to show it's a group, we're going to check all 4 of the group axioms. They've run off the slide here because I'm bad at editing these right now. But look at me not panicking, because I know the next slide has the proof that the Galois group is in fact a group. And you should try these out. You can, of course, you'll read them. I know you will. You're all good students. But you should try them out with an example like our function g from q adjoin zeta 3 to q adjoin zeta 3 that sends zeta 3 to zeta 3 squared. And just verify that all the properties work out. You might also want to bring f into the mix, the identity automorphism. For associativity, you might have to use like f and g to show that associativity works, because we don't actually have more than 2 in that Galois group. But that's okay. We can make sure that these guys actually work out the way that we think they should. Now notice there's no proof of g5 here. That's because often, in fact most of the time, the Galois group is not commutative. And here's an example on this slide. We've got in the middle the automorphism table that we built in chapter 14, and we're just going to see what happens to compositions in different orders when we plug in one element. Right? Switching the order of F3 and F6 produces different outcomes. And so I give you here this comprehension question. Why don't you see what happens when you compose them? Which automorphisms do you get, right? It's a group. It's supposed to be closed under this. So F3 composed with F6 should give you F1 through F6, one of those. Now the very last thing that I'll mention is that we use multiplication tables to write down what's going on with these things, or operation tables. So we can fill these things out in order to see what kind of structure a group might have. And that is your very quick and dirty introduction to groups. Please take a look at the worksheet that I've given you to do over this topic. It will give you a lot more hands-on experience with groups. Enjoy, and be well.